Hello and welcome back to the Ever Changing World podcast. I'm your host, Ava Zanetti, and today's episode has been well awaited. This has been a theme throughout my podcast for really the whole time that this podcast has existed. And this exact topic is, of course, the James Webb Space Telescope. I did a whole episode a really long time ago about the James Webb Space Telescope and what it hoped to do. I also spoke about its successor, the Hubble Space Telescope, which is similar but didn't have the breadth of technology and knowledge that we'd be able to use with it. And the James Webb Space Telescope was stressful since we weren't sure if it was going to, well, one, deploy properly and get out there. And really, our biggest worry was that the mirrors weren't going to work and all these things weren't going to line up, and it would have failed out into space where obviously astronauts and people can't start fixing it. The James Webb Space Telescope has been something that was in the works for like over 20 years and was in the works of so many astronomers and engineers and technicians and people on the job trying to get this thing out there. They knew that the Hubble Space Telescope wasn't enough and that we needed more to explore our ever expanding universe. The James Webb Space Telescope will help us understand the beginnings of our universe, looking at the Big Bang and looking at the expanding galaxy as well, and the galaxies that we see and why they're moving farther away from us. And because the James Webb Space Telescope can see in quotes so far, is because it's looking back at the early universe. And I will explain kind of how that works within this episode as well. So this is obviously a very exciting topic as it's been well awaited. The new images have come out, I would say, a few weeks ago. I believe it was in maybe a month ago already, but the images have come out from the James Webb Space Telescope, the original ones, and it's an exciting time to be alive. So many people worked on this, and so many people wanted to see this flourish, and we finally have images and we finally have things happening. So, looking at the images that had come out, I just want to make sure I get the date correct, of course, of when this had come out. There was obviously there's a primary mirror selfie in February, so we could see it, but the first image from Webb came out on July 11th, so almost a month ago to the day of as I'm recording this on August 9th, 2022. So this first image, which I'll speak about, was the deepest and sharpest infrared image of the universe ever. So when you compare this first image to the image that Hubble took not so long before, we can see a really interesting connection between the two. You can see the exact same star clusters, yet the Hubble one is a lot blurrier, and you can't really make it out well. While this James Webb Space Telescope one, obviously on my phone, it's not going to look as amazing as it would on a proper computer that can hold the proper specs on it. But we can see the beautiful galaxies. We can see how they are kind of clustered together in certain areas, and we can see so much, and it's actually insane. And Webb also captured this image in less than a day, while similar images from Hubble, which we have been using, can take weeks. So this new telescope is obviously a lot more efficient. We put billions and billions of dollars into it, so I would hope it would be a lot more efficient. So the image that I'm looking at right now is the first image if you want to pull it up yourself. The whole thing about it is that if you held a grain of sand to the sky at arm's length, the speck of that is the size of Webb's view here. So imagine just taking a grain of sand, putting it in your hand as small as it is, aiming it to the sky, put your arm out. That is what Webb has seen. So it's such a small piece of what Webb can actually observe. And it's insane that Webb even got into that small piece, as well as it's insane that our universe is that large, if you want to think about it that way as well. Our universe is absolutely huge, and of course it is ever expanding, ever changing as well. So some of these galaxies as well appear that they are bent. So why is this so? Well, the combined mass of the galaxy cluster acts as this almost gravitational lens, blending the rays from more distant galaxies behind it, which magnifies them. It's kind of like an illusion on our eyes. And this actually isn't the farthest back that we've seen, though. Non-infrared missions like COPE and WMAP saw the universe closer to the Big Bang, around 80,000 years after the Big Bang, where there was microwave backward radiation but no stars or galaxy. Webb sees a few 100 million years after. So how can we observe the past is the question. Well, we're observing the past using this microwave background radiation. So from the early universe, when the Big Bang happened and everything exploded and everything started forming, it left this background cosmic radiation, which we can actually observe. So it's the same thing as the Doppler effect with the redshift, where the Doppler effect is when you hear a car, right? So let's think of an ambulance. You're standing somewhere and you'll hear an ambulance. You hear it coming closer, goes wee, 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 wee. Like it starts, when it's close to you, it's really loud. Then it starts getting quieter, it leaves, or it gets louder as it comes. It's like, that was a really bad demonstration, but you get the idea. So this is the same thing with when we are looking at the light spectrum. So this idea of redshift is the farther back that the galaxies are, and obviously I'm going to make sure I get this right to make sure I get the scale right. The farther back the galaxies are, the redder it will be, and the closer they are, the bluer it will be. And that means that we are kind of looking at the past. So since light doesn't just instantly travel, it takes a certain speed to travel. It's as fast as anything can travel in our universe, or at least that we know of. But light, since it travels to us, even our own sun, it takes 8 minutes for the light from the sun to hit us. So we're technically looking at light that is 8 minutes in the past. Or 8 minutes old from where the sun is, right? So when we're looking at galaxies, it's the same exact thing. And when we are looking at redshift, because it takes such a long time for the light to come to us, these different things appear red, or appear blue, depending on how far back they are, because of this concept and because of how it is used. So I want to just make sure that I explained this properly. So yeah, to longer wavelengths. Yeah, so the farther back it is, the redder it will be. So when we're looking at these like galaxy clusters and you see kind of a reddish galaxy, you know that it's actually farther back. And this is, of course, when Hubble discovered that the universe is expanding, and we know that things are moving away from us. So as it moves farther away, it's going to get more and more red. And if it was coming closer, it would be more and more blue. So this is why we call it redshift, because everything is moving farther away from us. Because since the Big Bang, the explosion, however that began, everything started shifting. So then this cosmic background radiation plays into this redshift. So we can see that the universe is expanding with this redshift. With the cosmic microwave background, it's this leftover radiation from the Big Bang. So as the theory goes, when the universe was born, it underwent rapid inflation, expansion, and cooling, and then there is this leftover radiation that we can still see. So this is how we can determine how old the universe is in and of itself, and also determine other things in the universe and how old those things are. So the farthest back that we have seen is just 380,000 years after the Big Bang. And that seems like a really, really long time, because human civilization has only existed for around 200,000 years. So it seems like a really long time that, after the Big Bang. But realistically, since the universe is about 14 billion years old around, it's actually a really short time frame, which is really nice. And we've been able to see really, really far back. But obviously, because of that time, there were no galaxies. So if the James Webb Space Telescope looked that far back, there would be no galaxies for us to see, since it's just so far back. So that's why it's looking a few 100 million years after. So that was the first image, which we saw a lot with, and we can understand a lot with. So that was our very, very first image, which was really cool to see. And our second image was shortly after, which I'm just going to pull up. So our second one, we can see some beautiful spiral galaxies. So this next image is called Stephan's Quintet. If you want to see any of these images, by the way, you can either go on Instagram and you can see them. Just look up James Webb Space Telescope first images and you'll see a bunch. NASA is where I'm looking at right now on their Instagram. As well, all of the images are on NASA's website, which also you can look at. Which I might also explain a little bit more using their resources here. So this next image here is Stephan's Quintet. So these are 5 galaxies, 4 of which are interacting. So this left galaxy in the group is actually much closer to us than the rest of the group, which is really interesting. So we don't really notice this perspective, but it's this quintet. So these are actually colliding galaxies. So if you didn't know, our neighboring galaxy, the Andromeda galaxy, is actually going to collide and merge with us eventually, in a really, really, really long time, like way after humans kind of thing. But it is going to collide with us, and it's going to become one larger galaxy. So this is what these galaxies are actually doing right now. And they're colliding, and they are pulling and stretching each other into this kind of gravitational dance, where their gravities are almost interacting with each other. So Webb will actually revolutionize our knowledge of star formation and gas interactions within. So we do have a basic understanding of how stars are formed and all these different things, but when we can observe things in our current time and seeing them as they happen, we get a much better idea of the life and death of things and all of that. So this mosaic is the largest image to date from Webb as of July 12th, so I don't know if that's changed. But it covers an area of the sky 1/5 of the moon's diameter, as seen from Earth. It contains more than 150 pixels, constructed from around 1,000 image files. And of course, this means that Webb is the most complex and powerful space telescope ever built. We put a lot of work into Webb, and it has obviously paid off. So all of these they appear that they are touching. So although it was called a quintet, really only 4 of them are truly in this cosmic dance. Well, some are in the foreground. So these kind of proximity of these gives us astronomers a ring-side seat for witnessing the merging interactions between galaxies that are so crucial to all of galaxy evolution. Again, we are still really confused about how galaxies are formed, how stars are formed, how all of these different things formed, and this is giving us a lot of insight. Really do scientists also see how much detail interacting galaxies trigger star formation in each other, and how the gas in these galaxies are being distributed. So Stephan's Quintet is a fantastic kind of quote-unquote laboratory for studying these processes fundamental to all galaxies. So as well, tight groups like this may have been more common in the early universe when they were superheated. So when there's a bunch of particles all dancing around and it was a lot more stressful and a lot more things were happening, everything was closer together, things might have formed a little bit faster, a little bit better, and, more complex. Now as the universe is expanding and cooling as it expands, it's, everything's kind of spreading out, all the heat spreading out. It's not doing these crazy things as much. So infilling material may have fueled very energetic black holes called quasars, which you might have heard of. Even today, the topmost galaxy in the group harbors an active galactic nucleus. So this is a supermassive black hole 24 million times the mass of the sun. Again, I'm going to restate that because it's insane. It is a supermassive black hole 24 million times the mass of the sun. As we know, or as we believe there is a black hole in the center of pretty much every galaxy, including our own. So when you think of it, the moon orbits us, and all our little satellites that we throw out there, we orbit the sun. The sun kind of orbits its own little group within the galaxy, but really ultimately the sun is orbiting through the galaxy. So we're moving. We're not only spinning on the Earth, we're not only spinning around the sun, we are spinning around the Milky Way. And if we ever lived, long enough, hundreds of millions of years, we'd be able to see a totally different set of stars as we'd be on another side of the galaxy. And so, of course, if we're orbiting something, there has to be something in the middle that we're orbiting. And of course, this would be a black hole, which Stephen Hawking did tons of, research on. And unfortunately, never saw the first image of a black hole. That was also very exciting. That was a few years ago, 3 years ago, I believe now. But we are orbiting a black hole. So this galaxy has a supermassive black hole that is, absolutely insane in size. The galactical black holes are very large, as they need to have a gravitational pull that's large enough to pull all of these different, solar systems and star systems and all of these different things. So it's actively, this supermassive black hole is actively pulling in material and puts out light, energy, of course, because, you have to emit energy as well, that is equivalent to 40 billion suns. Again, 40 billion suns. So Webb studied the active galactic nucleus in great detail with the near-infrared spectrograph and mid-infrared instrument, or MIRI, and these instruments integral field units, which are a combination of a camera and a spectrograph, provided Webb with a data cube, or collection of images of the galactic core's special features. So, much like the MRI machine in medicine, the IFUs allow scientists to slice and dice the information in many images for detailed study. So not only we get to see this beautiful one big image, we also get to look at little pieces of the galaxy so we can better understand certain parts of it. So Webb pierced through the shroud of dust surrounding the nucleus to reveal hot gas near the active black hole, measure the velocity of bright outflows. The telescope saw these outflows driven by the black hole in a level of detail never seen before. As a bonus, Webb revealed a vastity of thousands of different background galaxies, reminiscent of the Hubble's deep fields. So that was our second image, which is also very interesting, of course. Another image that we saw that was really big, and I want to do this in chronological order, so I'm just going to go off of more images. Let me see. Where's our next image from Webb? I don't know. Let me look. We have a lot of Mars pictures. Okay. Hubble, of course, has beautiful images, but we are more interested in Webb. Okay, this next one I want to get. Okay, the NASA website doesn't have it, so I'm going to talk about this one. So this is a cartwheel galaxy, as seen from Webb. This is on NASA's Instagram if you want to go look at it. So this does not offer just a snapshot of the galaxy's current state, but we also see a peek into its past and future. So we believe that this galaxy that we took this image of is really beautiful. It's, if you aren't looking at the image right now, beautiful kind of pink with, it looks like a spiral, if you can imagine that. So we believe that this galaxy started off as a spiral galaxy before it collided with a smaller galaxy hundreds of millions of years ago. So it's now made up of two rings, a bright inner ring and surrounding colorful ring, which you can see if you look at the image. Both expand outwards from the center like pond ripples, so it creates this kind of spiral, interesting effect. The image is a composable view that combines the data from two of Webb's instruments, including one of those MRI machines. And this one camera reveals previously unseen young stars, while the MIRI reveals regions rich in hydrocarbons and chemical compounds, as well as silicate dust, similar to dust on Earth. So when we are looking at this spiral galaxy, we can detect a lot about how these galaxies are formed, why this one was formed the way it was formed, and all the intricacies within that. So that's another really interesting image from Webb, of course. The next image from Webb is, I don't know where it is right now. The next image from Webb was another nebula, which this is the right, okay. NASA, this one does have it. As well, the nice thing is that you can download all of these, to make it look nice, etc. You can download these. Okay. So, this Webb image captures a dying star in its final, quote-unquote, performance in fine detail. This is a beautiful, beautiful image. So, NASA James Webb Space Telescope has revealed details of the Southern Ring Planetary Nebula that were previously hidden from astronomers. Planetary nebula are the shells of gas and dust ejected from dying stars. Webb's powerful infrared view brings this nebula's second star into full view, along with exceptional structures created as the stars shape the galaxies and dust around them. New details like these from the late stages of a star's life will help us better understand how stars evolve and transform their environments. These images also reveal a cache of distant galaxies in the background. Most of the multicolored points of light here seen are galaxies, not stars. So we can see a bunch of, like outside of the nebula, we can see a bunch of bright, what they look like stars, but they are actually galaxies. But what we're looking at in the middle here is a dying star, which is an insane, of course, beautiful view. So this was one of the last images that Webb has sent out so far. So the dimmer star at the center of this scene has been sending out rings of gas and dust for thousands of years in all directions. And NASA's James Webb Space Telescope has revealed for the first time that this star is cloaked in dust. So again, when we're looking at this image, you can see right in the middle is this like really bright looking star, and we can see that we now know that it's spewing out all of this gas, which creates this really beautiful and interesting, intricate design in a way. And then when we look at the right, we can see the infrared view where we actually see, yes, it is this star, and we can see how it looks and where it's warmer, etc. So 2 cameras aboard Webb capture the latest image of this planetary nebula, cataloged as NGC 3132, and it's kind of informally known as the Southern Ring Nebula. Is approximately 2,500 light years away. So Webb will allow astronomers to dig into many more specifics about planetary nebula like this one, clouds of gas and dust expelled by dying stars, which of course is a very interesting concept, since looking at the birth and death of stars will help us understand our own star better, what stage our star is at, all of these different things. They can even help us with things like the climate crisis on our own Earth and how we can utilize certain things from our own sun, using some interesting technologies that we could develop in the recent future, which can be another podcast episode. So, understanding which molecules are present and where they lie throughout the shells of gas and dust will help researchers refine their knowledge about these objects. So this observation shows the Southern Ring Nebula almost face on. But if we could rotate it to view edge on, its three-dimensional shape would clearly look like 2 bowls placed together at the bottom, opening away from one another with a large hole at the center. 2 stars, which are locked in tight orbits, shape the local landscape. Webb's infrared image create new details in this complex system. The stars and their layers of light are prominent in the image from Webb's near-infrared camera, which is the NRI cam on the left, while the image from Webb's mid-infrared instrument, or once again, our beautiful MIRI machine, on the right shows for the first time that the second star is surrounded by dust. The brightest star is at an earlier stage of its stellar evolution and will probably eject its own planetary nebula in the future. So it's basically sitting beside this one that is expelling its planetary nebula, and it's almost there at its point as well, so they almost be together. In the meantime, the brighter star influences the nebula's appearance. As the pair continues to orbit one another, they quote-unquote stir the pot of gas and dust, causing asymmetrical patterns, which we can see here, and why it looks so interesting is these 2 stars are actually orbiting each other, which is super interesting. Each shell represents an episode where the fainter star lost some of its mass. The widest shell of gas toward the outer areas in the image were ejected earlier. Those closest to the star are the most recent. Tracing these ejections allow researchers to look into the history of the system. Observations taken with the NRI cam also reveal extremely fine rays of light around the planetary nebula. Starlight from the center star streams out where these holes are in the gas and dust like sunlight through gaps in a cloud. So it's almost creating this really interesting, it's spewing this out with just this hole in the middle, and you can imagine it just seeing light throughout that. So the planetary nebula exists for tens of thousands of years. Observing the nebula is like watching a movie in an exceptionally slow motion. So it's not just like it blows up and it goes away. It's slowly blowing up, if you want to think about it that way. Each shell the star puffed off gives researchers the ability to precisely measure the gas and dust that are present within it. As the star ejects shells of material, dust and molecules from within them, changing the landscape even as the star continues to expel material. This will eventually reach the areas around it, expanding what is known as interstellar medium. Since it's very long-lived, the dust may end up traveling through space for billions of years and become incorporated into a new star or planet. Thousands of years, these delicate layers of gas and dust will dissipate into the surrounding space. And of course, we are so far from it that it is not a worry at all within our own lifetimes. So the next image, or the grand finale, which I want to get to here, is the Carina Nebula. I believe is how I pronounce it, Carina. And then there's one more really interesting thing here about a planet, an exoplanet, which I do also want to talk about in today's episode. Okay. So this next one are these cosmic cliffs. You've probably seen this image around, but it's very, very beautiful as well. These are the cosmic cliffs, glittering landscape of star birth. So, NASA's James Webb Space Telescope reveals emerging star nurseries and individual stars in the Carina Nebula that were previously obscured. Images of quote-unquote cosmic cliffs show Webb's camera's capabilities to peer through cosmic dust, shedding new light on how stars form. Objects in the earliest rapid phases of star formation are difficult to capture, but Webb's extremely sensitivity, spiral resolution, imaging capability can chronicle these elusive events. So this image kind of looks like mountains and valleys, speckled with glittering stars. It's actually the edge of a nearby young star-forming region in the Carina Nebula. Captured in infrared light by NASA's James Webb Space Telescope, this image reveals for the first time previously invisible areas of star birth. Called the Cosmic Cliffs, Webb's seemingly three-dimensional picture looks like craggy mountains on a moonlit evening. In reality, it's the edge of a giant gaseous cavity within the NGC 3324, and the tallest peaks in this image are about 7 light-years high. The cavernous area has been carved from nebula by the intensive ultraviolet radiation and stellar winds from extremely massive, hot young stars located in the center of the bubble above the area shown in this image. The blistering ultraviolet radiation from the young stars escaping the nebula's wall by slowly eroding it away. Yes, it can do that. Dramatic pillars tower above the glowing wall of gas, resisting this radiation. The stream that appears to rise from the celestial mountains is actually hot ionized gas and hot dust steaming away from the nebula due to the relentless radiation. So this is why we're forming these kind of mountain images that we see within the image, and it looks like it should just be there, but it's actually because of this erosion. Webb reveals emerging stellar nurseries and individual stars that are completely hidden in visible light pictures. Because of Webb's sensitivity to infrared light, it can peer through cosmic dust to see these images. Protostellar jets, which emerge clearly in the image, shoot out from some of these young stars. The youngest sources appear as red dots in the dark, dusty region of the cloud. Objects in the earliest, rapid phases of star formation are difficult to capture, but Webb's extreme sensitivity, spiral resolution, and imaging capability can chronicle these elusive events. These observations in the NGC 3324 will shed light onto the process of star formation. Star birth propagates over time, triggered by the expansion of the eroding cavity. As the bright ionized rim moves into the nebula, it slowly pushes into the gas and dust. The rim encounters any unstable material. The increased pressure will trigger the material to collapse to form new stars. Conversely, this type of disturbance may also prevent star formation, as well as the star-making material is eroded away. This is a very delicate balance between sparkling star formation and stopping it. Webb will address some of the great open questions of modern astrophysics. What determines the number of stars that form in their certain region? Why do stars form? What certain mass? Etc., etc. Webb will also reveal the impact of star formation on the evolution of gigantic clouds of gas and dust. And the effect of massive stars with their violent winds and high energy is often apparent. Less is known about the influence of more numerous low-mass stars. As they form, these smaller stars create narrow opposing jets seen here, which can interact a lot of momentum and energy into the clouds, which reduces the fraction of nuclear material that seeds new stars. So up to this point, scientists had very little data about the influence of a multitude of young and more energetic low-mass stars. So with Webb, we've actually been able to understand this and obtain a full census of their number and impact through nebula. Located around 7,600 light years away, NGC 3324 was imaged by Webb using again the NRI CAM and MIRI. So the NRI CAM, with this really crisp resolution, unveils hundreds of previously hidden stars, and even numerous background galaxies, which we can observe and understand. In the MIRI's view, young stars and their dusty planet-forming disks shine brightly in the mid-infrared appearing pink and red. MIRI reveals structures that are embedded into the dust and uncovers the stellar sources of master jet and outflows. With the MIRI, the hot dust, hydrocarbons, and other chemical compounds on the surface of origins glow, giving the appearance of jagged rocks. NGC 3324 was first catalyzed by James Webb, actually in 1826. Visible from the southern hemisphere, is located in the northwest corner of the Carnegie Nebula, which resides in the constellation Carina. The Carina Nebula is home to the Keyhole Nebula and the active, unstable supergiant star called Eta Carinae. So this is really interesting since we've actually been observing this nebula for hundreds of years, and now we're able to see in this crisp, really interesting way where we can truly understand the nebula, understand how these young stars are interacting with the nebula and kind of creating and eroding this shape. It makes this really mountainous view. So the final image that was also really big is the atmospheric composition image, which Webb was able to reveal steamy atmosphere of a distant planet in detail. So we're looking at exoplanets here, and what an exoplanet is a planet outside of our own solar system. So anything that isn't, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, or whatever within our solar system. And exoplanets to have life, right? For anything to harbor life, it has to be within this thing we call the Goldilocks zone. So if you think of the classic fairy tale of Goldilocks, she can't have porridge that is too hot or too cold. And that is exactly what we need to sustain life. Earth, lucky enough, was within the Goldilocks zone, and that's why we are even alive today. It's not too cold on the Earth, and it's also not too hot to harbor life. And it's kind of in this perfect little area. And that leaves exoplanets. We want to look at exoplanets that are kind of in this perfect little area. One solar system that is quite good for this is the TRAPPIST-1 solar system, where we believe there are a lot of exoplanets that are within this Goldilocks zone, or at least it seems more promising. And with this image, Webb was able to reveal a steamy atmosphere of a distant planet in detail, which was in the exoplanet WASP-96b. Yes, we like to use really weird images and stuff for this. And within this, we can see, using the wavelength of light, we can actually see what water or H2O is on the planet. And that's a really interesting way that we can use images and infrared images to determine if there's life on other planets, etc. So Webb's enormous mirror, precise instruments join forces to capture the most detailed measurements of starlight filtering through atmosphere of a planet outside our solar system to date. Spectrum of light, which contains information about the makeup of a planetary atmosphere 1,150 light years away, reveals a distinct signature of water. The strength of the signal that Webb detected hints at the significant role that the telescope will play in search for potentially habitable planets in coming years. Webb's powerful new view also shows evidence of haze and clouds that previous studies of this planet did not detect. So we've been able to detect this distinct signature of water as well as this evidence of clouds and haze. And also atmosphere surrounding a hot, puffy gas giant planet orbiting a distant sun-like star. The observation, which reveals the presence of specific gas molecules based on tiny decreases in the brightness and precise colors of light. Super interesting stuff that we can even do this. It's the most detailed of its kind to date, demonstrating Webb's unprecedented ability to analyze atmospheres hundreds of light years away. While the Hubble Space Telescope has analyzed numerous exoplanet atmospheres over the past 2 decades, capturing the first clear detection of water in 2013, whose immediate and more detailed information marks a giant leap into the quest to categorize potentially habitable planet systems beyond Earth. So WSP-96 is one of more than 5,000 confirmed exoplanets in the Milky Way, located roughly 1,150 light-years away in the southern sky constellation Phoenix. It represents a type of gas giant that has no direct analog in our solar system, with a mass less than half that of Jupiter and a diameter 1.2 times greater, which is a really interesting dynamic. WSP-96b is much heavier than any planet orbiting our sun. So it doesn't even have the mass to back it up. It's just a large planet. And with a temperature greater than 1,000 degrees Fahrenheit, it is significantly hotter. WSP-96b orbits extremely close to the sun-like star, just 1/9 of the distance between Mercury and the sun, completing one circuit every 3.5 Earth days. So it's not only large and hollow in a way, it is spinning very, 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 very fast. The combination of large size short orbital period, puffy atmosphere, and lack of contaminating light from objects nearby, the sky makes WSP-96b an ideal target for atmospheric observations. So on June 21st, Webb's NRISS measured light from the WSP-96 system for 6.4 hours as the planet moved across the star. The result is a light curve showing the overall dimming of starlight through the transit and a transmission spectrum revealing the brightness change of individual wavelengths of infrared light between 0.6 and 2.9 microns and 8 microns. While the light curve confirms properties of the planet that have already been determined from other observations, the existence in the orbit of the planet, the transmission spectrum reveals prismatically hidden details of the atmosphere. The ambiguous signature of water, indications of haze, and evidence of clouds that were thought to not exist based on prior observations. A transmission spectrum is made by comparing starlight filtered through a planet's atmosphere as it moves across the star to the unfiltered starlight detected when the planet is beside the star. Researchers are able to detect and measure the abundances of key gases in a planet's atmosphere based on an absorption pattern, locations and heights of peaks on the graph. In the same way that people have distinctive fingerprints in DNA sequences, atoms and molecules have characteristics and patterns of wavelengths that they absorb. So the spectrum of WSP-96b captured by this machine is not only the most detailed near-infrared transmission of a spectrum of an exoplanet atmosphere captured to date, but it also covers a remarkably wide range of wavelengths, including visible red light and a portion of the spectrum that has not been previously accessible from other telescopes, which has wavelengths longer than 1.6 microns. This part of the spectrum is particularly sensitive to water, as well as key other molecules like oxygen, methane, and carbon dioxide, which are not immediately obvious in WSP-96b spectrum, but which should be detectable in other exoplanets planned for observation by Webb. Researchers will be able to use the spectrum to measure the amount of water vapor in the atmosphere, contain the abundance of various elements like carbon and oxygen, and estimate the temperature of the atmosphere with depth. They can use this information to make inferences about the overall makeup of the planet, as well as how, when, and where it was formed. The blue line on the graph is a best fit model to take account the data, as known as properties of WSP-96b and its star, example size, mass, temperature, and assumed characteristics of the atmosphere. The exceptional detail and clarity of these measurements is possible because of Webb's state-of-the-art design. Its 270 square foot gold-coated collects infrared light efficiently. Its precision spectrographs spread out into the rainbows of thousands of infrared colors, and its sensitivity infrared detectors measure extremely subtle differences in brightness. So this machine, the NRISS, is able to detect color and differences in the brightness between those colors and of a few hundred million parts per million. In addition, Webb's extreme stability and its orbital location around Lagrange 1.2, roughly a million miles away from the contaminating effects of Earth's atmosphere, makes for an uninterrupted view and clean data that can be analyzed relatively quickly. The extraordinarily detailed spectrum made simultaneously by analyzing 280 visible spectra captured over observation provides just a hint of what Webb has in store for exoplanet research. For the coming year, researchers will use spectrography to analyze 1/4 of Webb's Cycle 1 observation time is allotted for studying exoplanets and the materials that form them. The NIRISS observation demonstrates that Webb has the power to categorize the atmosphere of exoplanets, including those of potentially habitable planets, in exquisite detail. So looking at all of those images that I mentioned that I hope you will go look at, I will link this in the bio of today's episode. I hope that you learned something about the James Webb Space Telescope. There are so many images that have come out, and I can't wait for even more images to come out, and probably do another episode if there's enough images to talk about. And, truly the James Webb Space Telescope is revolutionary. It is way ahead of its time. We've been working on this thing for decades, and it's only right that we have something proper up there in space that is actually going to teach us about our universe and help us understand at least what the future is. Maybe not where we come from and how it all began, but at least the future of space-time and how all these things work. And I find that is going to be the most vital part going into the future using Webb. We're going to have to look at exoplanets. We're going to have to look at all of these different things. And it's going to be really interesting. It's going to be fun. There's going to be a lot of, scientists and astronomers on board that are actually going to change the world in this way. And they are going to do so in such a wonderful, interesting, and engaging way. So all in all, I just want to thank you all for listening to today's episode. I hope that this has sufficed. I hope that I have given enough information, enough interesting information in today's episode. I hope you learned something about the James Webb Space Telescope. It's such a great telescope. I absolutely love it. And I hope you all can please connect. We have Forever Changing World in Instagram, which is ever.changingworld. Again, ever.changingworld. The Twitter is everchangingwor. Again, everchangingwor. The website is shows.acast.com/ever-changing-world. Again, shows.acast.com/ever-changing-world. Thank you so much for listening. Please tune in next week for another amazing episode where you will be learning once again. Thank you for listening, and the world is always changing.